Hi. This presentation provides an overview of how to enable effective teaming between humans and machines to support and enable future aviation. Aviation is slowly reaching its limits with current systems and control methods. The hope is that the only way to manage increasing demand for airspace is by involving artificial intelligence applications and agents to support human operators. Modeling human-machine interactions is the first step towards enabling smart aviation, but also the most challenging aspect. The approach we propose, the Flight Information Digital Twin Platform, enables aviation human-machine teams by providing a virtual flight environment in which various agents, whether human or machine, join the environment through their own avatar-like application. The Information Digital Twin. Human, agents and systems roles can then be modeled using the same language and according to the same rules for exchanging and evaluating information. The Flight Information Digital Twin Platform's central component contains the flight reference model that captures the dependencies and correlations of all flight variables. Each information digital twin relies on the flight reference model to define a local, role-specific model of the agent or human it supports. Every action any agent performs updates its local model, which updates the reference model. The aircraft-specific flight reference model is part of an air traffic information model used to manage a complete flight zone. These updates ensure that all agents are aware of the flight status and can change their actions accordingly. How does the Information Digital Twin accomplish its objectives? The Information Digital Twin consists of three primary components. A representation component containing a subset of the flight information model which captures the variables' dependencies and correlations unique to an agent. Next, a reinforcement learning component that models the agent's role and, given a particular input, generates potential action trajectories and recommendations. The reinforcement learning agent queries the representation for each input to compile the parameters necessary to update the model and define its recommendations. The continuous interaction between the two components allows the Information Digital Twin to modify action trajectories in response to the flight's progress. The States and Actions Synthesizer is the third and most crucial component of the Information Digital Twin. This component relies on machine learning algorithms that learn the dependencies and correlations of the variables in the agent representation and their changes over time, and then recommend or update the states and actions in the reinforcement learning model accordingly. What distinguishes the Information Digital Twin platform? It is how the platform represents the flight environment, or, more accurately, how it defines the units of calculation or the environment's information tokens. To understand why the Information Digital Twin platform is unique and what we mean by information tokens, let's consider ChatGPT, a prominent example of using artificial intelligence for natural language processing. To model a language, that is, to define the correlations between its various elements, it is first necessary to specify these elements or the basic units of text that can be modeled or tokens. On average, a GPT token equals 0.75 of a word. For example, the word hamburger is made up of three tokens: ham, bur, and jur. Once these tokens are defined or learned, it is possible to model a language by defining the correlations between its various tokens. Using the 51,200 tokens, ChatGPT then analyzed around 500 billion tokens and learned 175 billion relationships between them. The question of how to use artificial intelligence to manage a complex domain is answered by first defining the consistent alphabet, features or information tokens used to exchange information within the domain. Only then is it possible to apply AI methods to learn patterns within these tokens and model the domain. That is, to model human-machine teams, we must first define the language used by the team members to exchange information. Defining the domain-specific tokens, or information tokens more precisely, is the primary innovation and emphasis of the Information Digital Twin platform. The information tokens used in the Information Digital Twin platform are made up of an input-action-output triplet. In terms of communication, the triplet is made up of a sequence of a sent message received response corresponding response, which is the minimum number of messages necessary to evaluate the communication effectiveness between a sender and a receiver. An AI instance seeing two agents interacting can determine that each time agent A sends message X to agent B, it receives answer Y. So, it learns that agent B associates the receipt of message X with response Y. Yet, the AI agent cannot say anything about agent A, e.g., did expect message Y back, or it still expects a different message from agent B. Only by observing agent A reaction to message Y can it tell something about agent A, e.g., if message Y is intended or not. That is, in this interaction instance, the AI can only learn about the interaction information of the two agents by observing the triplet of sent-response reaction. Capturing the significance of an interaction is thus only possible by considering at least this triplet: input, action, output. In a complex environment, the number of possible information tokens can be vast. However, most information tokens will occur with low probabilities and can thus be marginalized. Similarly, in GPT-3, the number of possible tokens across the multiple languages in the model can be extremely high. However, only 51,200 tokens have been found relevant for extracting meaning. Creating domain-specific tokens is an essential step for modeling domain interactions. Nevertheless, other parameters are required to represent the domain's dynamics and evolution. To capture the interaction's dynamics, the Information Digital Twin platform assigns two values to each information token. The first parameter is the token information value measured in bits, which reflects the token's significance to the environment's numerous interactions. For example, for a specific medical condition, how often using medication X changes a patient's temperature from T1 to T2. In analogy, the letter E in English would have a higher information value than the letter Q since E is used more often. The second parameter is the token Bayesian information value, likewise, measured in bits. This value indicates the significance or relevance of an information token for a particular interaction goal, or final state in terms of reinforcement learning. For instance, specific financial trading information tokens may be more pertinent to maximizing portfolio value than minimizing transaction risk. Every action performed by any agent in the environment modifies both values for every information token. As an analogy, imagine that within the next 10 years, people everywhere cease eating, preparing, and selling hamburgers. Hence, the word hamburger will be used less frequently. Therefore, the correlations between the three tokens ham, bur, and jur will decrease in the subsequent GPT model updates. Additionally, correlations between the word hamburger and McDonald's or Burger King will decline, reflecting the environment's dynamic as hamburger becomes less relevant to daily life. How to start? By defining the task-related information tokens. Here is an example of a simple agent that seeks its environment for food. To improve its decision-making, it creates a lookup table to record its findings. After encountering several objects, it begins to notice that round objects yield less energy than long objects and that blue objects should not be consumed. Each of these findings is assigned an information value that indicates the frequency with which it occurred. To improve its decision-making, the agent identifies objectives, such as searching for high-energy food. In this case, the token Bayesian information displays the relevance of each feature, and the token composed of three features to the goal. Hence, consuming yellow, long objects provides high energy. If yellow, long, and high energy objects are regularly present in the agent's environment, the agent's state synthesizer groups these characteristics under a single object, a banana, with a specific information value. The table and the associated information values then help the agent decide which features and information tokens are relevant to its objectives. For instance, the banana has a higher information value for the agent on the right, indicating that bananas are more pertinent to its activities than for the agent on the left, which cannot consume bananas and can only record them as yellow, long objects. Consequently, they have no use for it, and it is not part of its objectives, so its Bayesian information value is 0. In contrast, the agent on the right searches for and consumes bananas. Therefore, the banana has a positive Bayesian information value indicating its utility value to the agent. Defining a standard set of information tokens with corresponding measurable information values enables agents to exchange their experience and knowledge, which lead to faster learning and information transfer within the team, and above all, enable predictions and increase communication and decisions effectiveness. We have completed the development of the representation component, which is offered as a web application. We are currently working on developing the reinforcement learning component. The states and actions synthesizer is the final and most sophisticated IDT component, and its development depends on analyzing a substantial amount of data. We are currently focusing on use cases in the financial and healthcare. How to mature an intelligent human-machine teaming environment like that of aviation. The first step is to define the language used in the environment, the standard shared set of information tokens that can be used by the various team members to represent and model their interactions and collaboration in a consistent way. Without a shared language, and no matter how sophisticated and capable are the various agents, their collaboration will be ineffective in the same way as a team of highly skilled technicians who speak different languages and try to communicate to solve a technical problem. However, with limited knowledge of a shared language, the team might end up solving the problem, but in a longer time and in much more communication cycles. Once the set of information tokens and their information values are primed, the next step is to define the subset of information tokens used by each agent to manage its tasks. Based on the various information token values, some profiles can then be defined to indicate preferred performance ranges or risks. The next step is to build the information digital twins reinforcement learning component for each IDT, which would monitor the agent actions and recommend best actions towards some objectives desired by the agent. The next step is to close the loop between the various agents and the reference information model on the platform level. The final step is to connect the aircraft-specific flight platform to the aviation-level control level. It should be clear that before this connection, an aviation set of information tokens need to be defined represented first. Identifying a set of information tokens representing how agents exchange information in the domain is the first step in enabling AI-supported domains. Once the set of information tokens is determined, it is possible to represent agents, their tasks, and their interactions consistently. The models of the various agents are then used to align them with domain-level objectives and integrate them across the domain. Thank you for watching.